Hello community! Today finally we have time to talk about a simple problem in AI, no? It is multitask optimization. So you know this, no? Today there is a new topic if you have a large language model, a vision language model, and you start to fine-tune it on your data. And you notice that something is happening, what we call catastrophic forgetting. Because if you now come with your data in the fine-tuning process, you notice that the model loses its ability to generalize after your fine-tuning phase. And you see, what is happening? Now, it turns out that also this is not just happening to our LLMs, but our VLMs models. So whenever they are now adapted to new tasks, their performance suffers. And we have especially this if we merge here multiple fine-tuned models into a new conglomerate. So what can we do? Let's look at ChatGPT and I say, hey, explain catastrophic forgetting when fine-tuning an LLM and show me the latest information. Is there anything on here on the page archive? Search the web. Now we have this new search the web functionality with ChatGPT. And I think at the end of October 24, are solutions available to prevent this catastrophic forgetting of AI? And comes back and says, well, yeah, mitigation scaling, yeah, beautiful sources. Okay, this looks interesting. Let's have a closer look. So we go here, catastrophic forgetting, also known as catastrophic interference, phenomenon machine learning, where the model loses here the previously acquired knowledge upon learning new information pronounced during the fine-tuning of LLMs, empirical studies from August of 2023. Okay, this is an old one, never mind. Second one is mitigation strategy. Okay, February 2024, a little bit more up to date. Scaling laws here, okay. Scaling laws for getting fine-tuning, January 2024. Okay, this is not the latest one, so course data of October 24. Significant challenge in fine-tuning LLMs. Several mitigation strategies have been proposed. Ongoing research, development of robust solution is crucial for the efficient development of LLMs. And I say beautiful. And I say, show me the latest AI research preprint on this topic from October 2024 only. Okay? And hey, I can even choose between two versions. What's the difference? Empirical study, August 2023. Catastrophic forgetting, June 2024. Instruction vector, June 2024. If this is the latest, no, this is definitely not the latest. Okay, this was version 1. Version 2, August 2023. This is not good. Then we have June 2024. Yeah, and again, June 2024. So this is about, 5 months old. So as of October, this new web search functionality finds things that are 5 months old. Okay, yeah, I'm not really happy, but this is it, what we get back from the new search functionality with ChatGPT. So I prefer this response. Let's go with this one. Beautiful. And I say, hey, search for a new archive preprint that includes here the new method to fight here catastrophic forgetting called Linus. And here in October 2024, a new method called Linus was introduced. Suddenly it finds here this beautiful selective parameter freezes, adaptive learning rates, regularization techniques. Okay. Yep. Catastrophic forgetting. Yeah, this is what we are looking for. Preventing the alteration during the new task learning. Lower learning rates, the parameter associated here. Yep. Significant advancement in continued learning in LLMs. Comprehensive understanding. And so it is sources. We look at the sources and we see these are old sources. No, 2017. Wow. Regularization. Oh God, 2017. I hope it is not sorted here. Yep, no, this is not it. December 2016. No, this is not it. 2021. Yeah, 2023. December 2023. Yeah, April 2024. Okay, June 2028. Yeah. And it's missing. Okay. So I say now, hey, give me the link to this preprint code Linus here. And now we have it, now we have a complete different title. So this was just here hallucination. Because now we have it here. Yes, Linus post-training, beautiful. This is the preprint. This is the new research we're going to talk about by Google and our beautiful institution in Switzerland. So with this beautiful insight, we come back and say, okay, so we have a huge pre-training data set, and then we have our pre-trained VLM. And sources tell us it costs about $1 million to $10 million, or maybe even more, to have this beautiful pre-trained VLM with all the video data and image data and the textual data. Great. And now you come with your fine-tuning and you say, hey, I have domain-specific data. Financial, chemical, biological, physical, whatever. And now you do your fine-tuning with your data. And you know what's going to happen? This fine-tuning now overrides here the weight tensor in the different layer of your pre-trained VLM with the fine-tuned new weight structures with the fine-tuned new weight tensors. And therefore you lose here the general knowledge of the pre-trained VLM, depending on the intensity and the complexity and how you do the fine-tuning. And here we have a beautiful new study, end of October 2024. Here we have a Swiss institution with Google, and they look at this and says, hey, you know, we have a simple idea. We do just some post-training layer scaling to prevent here the forgetting and to enhance here the model merging capabilities. So let's have a look at this. And you remember in this video, I used this simple analogon to show you here we have the pre-trained data and then we have some fine-tuned data. And I was talking about lowering this. But now let's focus on this and let's say, okay, so we have the pre-trained vision language model with our pre-trained weight tensors. And then we have some fine-tuned data. And now we see if we do the full fine-tuning methodology, beautiful, yeah? Everything is happening now. And in the different layers that we have now from our input, we have layer 1 in the transformer architecture to layer N, and then we generate an output. Great. Now, we know that in vision models especially, those shallow layers that are right next to our input layers here, they might recognize edges or textures, features that are useful for many types of images regarding here of the specific object that is being identified. In contrast to these shallow layers, we have the deeper layers, no? Those layers here down there. And those deeper layers become progressively more specialized. So fine-tuning their representation to your task-specific details, such as recognizing very distinct objects, like features like a face or a particular shape, this is where the deep layers come into play. Now, traditional fine-tuning treats all the layers equally, and often overriding this broad foundational representation with your data because you do the fine-tuning. And this here, the result is then again a catastrophic forgetting of the pre-trained vision language data. So how to handle this? Now the idea is simple, yeah? We have here these shallow layers and we have here these specialized layers. And if we have here the new fine-tuning data and we do here the training, you know what's gonna happen, yeah? Where you say, okay, the shallow layers in our neural network, whatever you use here in a VLM here, they're here the general knowledge. And the deeper layers, on the other hand, is here the specialized knowledge of our fine-tuning. If we say this is a hypothesis that we're going to work with, so what we have, so very close in the shallow layers to our input, we take care that we have our pre-trained tensor structures. Here, layer 1, these are our tensor structures from the pre-trained model. This is the general knowledge that the VLM has been trained on. We want this. We want a general knowledge of a vision language model. However, then gradually as move deeper and deeper in the layer architecture of our VLM, now we want that here doing the fine-tuning, here in green, we want to have here that this system adapts here to the specifics of the new tasks that we want to learn the VLM on the specialized knowledge. So we say, okay, so at the very deep task, I want that the fine-tuning weight structures are now dominant. So at Ln, n is now, I don't know, 100 layers or whatever you have. So at really the deepest layer you have close to the output, you say, and now I want here the weight structure of the fine-tuned. And you get the idea. In between now, you can go gradually here from your pre-trained data weight structure to your fine-tuned data weight structure. And you start to override here almost nothing, a little bit more, and in the end you say, yeah, now I want a complete override because this is now my new highly specialized knowledge from the fine-tuning. So you see, it's so easy. And now this lines approach here it is computationally efficient. This is the beauty. It is fast, as it does not require here altering the training or the fine-tuning process themselves. But it is a post-training step, and it is a simple post-training step because we just look here at the difference here of the pre-trained weight configuration and the fine-tuned weight configuration. And we just calculate a delta, and a delta of a vector is some simple arithmetic operation. So this is fast and beautiful. And in multitask scenarios, where the models trained independently on different tasks or they are merged, this methodology also demonstrates significant improvements. We have close to 99% of the original pre-trained knowledge in the weight structure is preserved, and close to 98% of the new fine-tuned data is also available here in our weight tensor configuration. Now, in those tasks here, where in these cases where we have these multitask scenarios, the update of the parameter is likely to interfere with each other, leading what we call here negative task inference. But now, applying this new idea of lines, we do the same layer-wise scaling technique to the merge parameters with the multitasks. This helps us now preserve the shared representation across multiple tasks and therefore improving here the overall model performance. And you might say, okay, so I have enough number of layers here that I can say, okay, so in the next layer I have task number 12 and then I have task number 14. And you override, and you see it becomes not as easy if you go in the multitask representation. So therefore, this is a nice idea. So Linus here maintains here the core knowledge here in the shallower layer structure, while allowing here the new information to be task specific from the fine-tuning of your VLM. Now, mathematically here the authors say if we denote the scaling factor for each layer, so the deeper we go, we have a scaling factor. Here, for example, it is almost close to 0. There's no overwrite here of the pre-trained weight structure. And then the deeper we go here, then we have almost a complete overwrite here. And this is here where our specialized fine-tuning knowledge resides. So, shallow layers, and called general features, deeper layers are better suited for task-specific learning. But careful now, no? These multitask inferences can be minimized also by adjusting the layer-wise scaling, especially when merging now multiple fine-tuned models trained on different tasks. So suddenly we go here from one VLM with multiple tasks to multiple VLM models that all have been fine-tuned on very particular tasks. And now this merging process you can also do here with the new lines methodology. But careful. Yeah, let's talk about the good thing. The beautiful thing here is simplicity. This lines methodology is computationally lightweight because it's a post-training adjustment. You just calculate the difference here between given here each specific step here of the different weights in the pre-trained and in the fine-tuned structure. Adaptability. It is effective across vision and language tasks, demonstrating your strong generalization on diverse test scenarios. Plus, it is complementary to existing methodology since it is simply a vector operation of a weight tensor. No? You can combine this with out-of-distribution generalization methodology, whatever you like. The ugly, the not so beautiful is, well, it is limited here to the layer scaling. No? Now, here in this paper we have a linear scaling that limits here the flexibility to adjust your specific interlayer features or dealing with task vectors that do not follow the layer-wise generalization. Because maybe a more complex task is split among multiple layers, and then here a simple layer scaling would fail. You say, no problem. Why should I have a linear function? I can have a much more complex function. So you see here we start to experiment with this. No? And assumes that shallow layers should be preserved for general tasks, which might not be universally applicable, especially if we have a high specialization across all the layers. This means that general knowledge might also move now in a very specialized direction. So you have to play now with your parameters, how much to override which layer structure, how deep it is in your neural network. So you have to do some experimentation to find out the best hyperparameters for this system. But of course, this is not an isolated system. We have alternatives. So this alliance methodology aligns here with model merging techniques, different model merging techniques like task arithmetics or ties merging. But if you want, it kind of extends them here to a layer-wise scaling, distinguishing it from models that do not leverage here the layer depth as the critical differentiator here in your fine-tuning process. So this approach, if you want, complements now much more complex methodology that employ, for example, a gradient-based merging, providing an efficient alternative also to model soups or to AdaMerging without an extensive training. So it is a fast, quick, and kind of a nice structure if you only have a single task or maybe 1, 2, 3 tasks. But if you go now in model soups here, you need maybe a little bit more powerful elements. Yeah, for the code, easy here. We have a GitHub repo here, beautiful. You find here the code and everything over there. And let's talk about it a little bit if you want to go a step further here about more complex methodologies, especially to combat here this catastrophic forgetting. I would like to recommend 2 papers to you, and this here is from end of May 2024, AdaMerging, adaptive Ada model merging for multitask learning. So we have here Northeastern University, University of Maryland, here Explore Academy, China, University of Oxford, UK, and the Nanyang Technology University in Singapore. This multitask learning methodology leverages here the entropy minimization. But here we have the complete code if you want to have a look at the code. So they go here now with this multitask learning here to empower here model to tackle multiple tasks simultaneously in one model. And recent development known as task arithmetic has revealed that several models, each model fine-tuned for here a particular special task, they can be directly merged into a single LLM or a single VLM to execute here the multitask learning without necessitating here a retraining process. So nevertheless, this direct add-on of models often leads to a significant deterioration in the overall performance of the merged model, and therefore AdaMerging here is a real nice but complex alternative. Users should know maybe about the second paper. I would recommend this one here. Now we are not going here with entropy, but we are here knowledge composition using task vectors. Here the task vectors are the difference vectors between our pre-trained weight structures and our fine-tuned learned tensors with learned anisotropic scaling behavior. University of Adelaide. Hello, Australia down under. Great to see this publication for you. Atlas, maybe you're familiar with this. And if you have a look at the study, please note that they also explore here LoRa, our parameter-efficient fine-tuning shortcut here, the low-rank approximation. And they also tell us here exactly what we found here in 2 videos ago here, using now a specific rank of LoRa in the task vector. And here a rank of 64 leads to a similar performance compared to learning the composition of only weight matrices in the standard task vectors. So here, just want to notice here, also here they argue here, hey, take a high rank of LoRa, do not go with 2, 4, or 8, or 16. Use a higher precision rank for the LoRa approximation, and then you will have no problems at all. Yeah. If you want to see my latest video here, where I have a deep dive here on the LoRa spectral properties and why we have to take care about the specific rank parameter when we do here a fine-tuning, this is the video for you. But please notice we do have here, if you want, a problem in the term definition, because the task vector is not the task vector in all other publications. The term task vector, unfortunately, is used for multiple phenomena in AI. So, if I have here this, one of my latest video about the spooky action in AI, and we also look here inside the vision language model, and UC Berkeley defines here task vectors, those task vectors from this video are completely different from the task vector that, for example, we copy here or we investigate here in this video here. So this study here, where are we? Come on. Yep, here we are. So this study here, our line study by our Swiss organization and Google DeepMind, when they talk about task vectors, it is completely different to what UC Berkeley is talking when they talk about task vectors. So watch out, because they use a similar term or the identical term does not mean that they also refer to the same complexity in a neural network or in an artificial intelligence system. So careful with the terms. Great. I think this is it for today. A beautiful last here information. This is the study if you want to bring you up to speed here to the latest AI research about coping here with catastrophic forgetting if you have multitask or multi-modal mergers. I think beautiful study. Have a look at this yourself, and it would be great to see you in my next video.